Hello. In this video, I want to give you a quick rundown on exam 1 for planetary astronomy. I'm going to tell you about the exam itself, how to prepare for the exam, and run through some of the major topics that we've covered in the last a month or so to get you up to speed on that. So, first up, the exam is on Canvas. It's an open book, open notes exam. And there's a couple of things that you want to be careful about with that. First of all, even though it's open book, it's a really good idea to study for it as if it was a closed book exam. You don't want to spend a lot of time trying to look things up during the exam time. So you want to make sure you can focus on just the stuff where you really need that. So treat it like it was a closed book exam. Try and make yourself really ready for this, and then you've got your notes, you've got the lectures in case you need them. All right. The other thing to know about this is what I want to see is your work. If it looks to me like you've been copying work from my lectures, from websites, from AI, anything like that, I'm going to have to take points off. So make sure that when you answer your questions, you answer them in your own words. I will, as I say, take points off. Sometimes I've even been known to give people zeros on exams. So try to, make sure you tell me what you understand, not what somebody else does. So the exam itself is going to be available on Canvas from 8 o'clock Monday morning through midnight on Wednesday. So you've got that entire time period in which to do the exam. But once you start it, you've got 2 hours to finish. So you want to pick a time when you've got when you can really focus and then get it started. Now, there aren't a huge number of questions. In fact, there's only 10 multiple choice questions and 3 written answer questions. So 2 hours should be lots of time. You should not feel a crunch for time on this at all. So let me give you a little rundown on these. First of all, make sure that you look at the exam 1 review sheet. That's on Canvas. It's in the modules, and that will give you a good sense of what's actually being covered in this exam. It also includes a study checklist, and that brings up a really important point here. When you're studying for an exam like this, you don't want to just be reading stuff or watching lectures. You want to make sure you're actually practicing. A lot of the exam questions you're going to see are going to be based on assignments we've done. And so you're going to need to know what to do when you see something looking like a Mystery Solar System question or a your turn question. So you want to practice those. And so I've given you a list of things that you can practice to prepare for the exam. Now, first off, the multiple choice questions. There's only 10 of them, as I said, and they cover a series of topics that we've already been through, starting with the size and scale of the universe and running right through to gravity and orbits. And if you look in the review sheet, you'll see it actually tells you what the topics are for each one of those questions. So make sure you go through that, and that'll give you a good idea of what to be studying for in that part, because you'll know the kinds of things I'm going to be asking you. Some of those questions may be questions you've seen on quizzes. Others are going to cover some of the ideas that we've seen in other kinds of assignments. But it's material we've spent a lot of time on. Okay, then we have the 3 written answer questions, and probably that's where you're going to want to spend most of your time. That's where most of the credit is on this exam. So don't spend 3/4 of the time doing just those 10 multiple choice. So the 3 written answer questions there are 3 different types of questions. The first one is what I call a review question. And that looks a lot like the note-taking questions that we've done in class, in the course. So things like describe the cause of the seasons, or Newton's laws of motion, or the different scales of the universe. So those sorts of things that we go over in those note-taking questions, that's what this is going to be about. Now you may get, one of those questions may ask you to draw a diagram, because you know some of the note-taking questions I've asked you that. If it asks you for a diagram, it will also have be in the form of a file upload question. And that means that you can give what I'm expecting you to do is probably you're going to want to just write your answer out by hand, and then create your diagram by hand, and then just take a picture and upload that. That's certainly for most people going to be the easiest way. You can do this on the computer if you want, if you have the time. But make sure, again, if you're doing a diagram, that it's your diagram. It's not something you cut and paste from somewhere else. Now, for the review questions, there's a list of note-taking questions that is given in the that's also given in the modules page. And so take a look at that, because those have my answers to those note-taking questions. So this will, and no, I don't want you to just copy my answers there when you're answering a question like that, but this gives you an idea. Make sure, try writing down your own answers to some of these things, and then check to see that you're getting all the key points there. So this is one you sort of have a pretty good idea of the kinds of things I'm going to ask you. The second one is what I call a critical thinking question. And so that's going to be like some of the your turn questions or some of the mystery solar system questions, not the ones that we've seen as where you have to actually sit down and do a major calculation, but you've seen a lot of other things like in week 3, we did some questions where you had to look at one of the planets in your mystery solar system, and see how its view of the sky changes over different periods of time, or look at the seasons. So questions like this that I might ask you under this critical thinking section. And there will be a mystery solar system table in the exam for you to look at. So make sure you're using that data table to answer that question. And then finally, there will be a calculation question. And again, based on the kinds of ones we've done in the mystery solar system assignments. And we've had 3 now. We did the light travel time, we did the acceleration based on an impact, and we just did weight on another world. So you've got 3 different options here, and the exam is going to, and you're going to see a question based on one of those 3. So again, practice a few of those. You've seen how to do these now, so get some practice in so that you're ready to tackle these. Okay, so the next thing I want to do is run through some of the major topics that we've looked at. And I'm really just going to hit some of the biggest, sort of most important ideas we've seen. I'm not going to go through every detail that we've covered in the last month and a half. But starting with size and scale of the universe. So that's a big chapter. That's a chapter with a lot of definitions. And so you really want to be comfortable here. You want to know what I mean by a planet, a solar system, a galaxy, a star, right? How big are these things? How far away are these things? And I'm talking about in general terms here, okay? Because there are many different sized planets, but planets are a lot smaller than stars, right? You should know that. Stars, the nearest stars other than our own sun, is going to be many light years away, okay? Even the closest one is about 4 light years away. And when you look up at the night sky, most of the ones you're seeing are tens, hundreds, even thousands of light years away. So that's the stellar scale, and you should have a sense of how big that is compared to the solar system scale. Because remember, our solar system is just the sun and the planets and the other little things that go around the sun, and that's much smaller. As you saw when you did the light travel time calculation, our solar system, it only takes hours to cross the solar system. Whereas when you're talking about going to another star, I'm going to say it only takes light hours to cross the solar system. It takes us a lot longer because we don't move that fast. Going to another star, even light takes many years to make the trip. That's what we mean when we say it is light years away. And then there's the galactic scale, which is even bigger. Our own galaxy, as we saw, is 100,000 light years across. So when you did that diagram of the Milky Way, and I had you plot a couple of things on them, they should all have been in one little tiny area on your diagram, because even a distant star like Eta Carina is very close to the sun compared to the size of our galaxy. So our galaxy has hundreds of billions of stars, and our sun is just one little one in all of that. So that's what I mean by the size and scale of the universe. And you want to get those kind of definitions down. We also did some math review in that chapter. We talked a little bit about how you deal with units, working with exponents, and certainly doing word problems like the ones we've been doing. So I should say right now, if you've been struggling with those, you really want to make sure now, before you actually start taking the exam, that you get that down. And that could mean spending time with the tutorials. That could mean spending time with me. If you want to send me an inbox message and have us go through that and make sure you know how to enter those exponents in the calculator, how to put those things in the algebraic formula, send me a message. Okay, let's set up a time to do that. That's one of the key things I have time to do, and I want to help you. I want you to learn how to do this. So that was the first chapter, and it's a pretty big one. An even bigger chapter for us was the motion of the earth and sky. And that's where we really looked at what it's like to be on a moving planet. Okay, the earth spins, the earth orbits, and we spent a lot of time talking about how our view of the sky changes and how that's connected to those motions of the earth. And so we talked about the daily motion, the rising and setting, and how that changes depending on where on the earth you are, whether you're at the equator or at the poles, or like most of us, in between those two. We looked at how how the fact that different planets have different spin rates and different orbit periods. And you did some assignments where you tried to tackle what that means and how that's going to, how that affects the view of the sky, not just here on the Earth, but on any planet. We talked about seasons. And seasons is one of those classic things that astronomy teachers always like to ask about. So you should certainly have a good sense of what causes seasons. You should be able to draw a picture of that. And you should be able to talk about how the seasons might be different on a different planet. What causes that? Remember, seasons are about tilt, not distance. And so it's the tilt you're going to be looking at to try to determine how extreme the seasons are on a planet. We also talked about the moon, and the moon orbits the Earth, and we looked at the phases of the moon. And remember, those are caused by how much of the sunlit side of the moon we can see as it orbits around us. And so we looked at that. We also looked at eclipses. And eclipses are when the Earth casts a shadow on the moon or the moon casts a shadow on the Earth. So that's another key topic. And don't confuse the two, okay? Moon phases are not caused by shadows, but eclipses are. Okay, then we had a really short chapter, just a very quick lecture on the process of science. And the key thing that was built around was the idea of scientific hypotheses. And so, what does it mean to make a hypothesis? How do we test those hypotheses? That's really what that one was about. You're not going to see a lot of questions on this topic, but there should be. You'll get at least one out of it. Okay, then we got to the two big physics chapters we looked at. First of all, motion and energy, and this is where we started really trying to understand the world from a physical science point of view. So we talked about things like speed, velocity, acceleration, and acceleration is a tricky term, and partially because we use it different ways in different parts of life. Here in science, acceleration is specifically a change in either speed or velocity. So that means that something is only accelerating if its speed is changing or if its direction is changing. If something's going in a straight line at a constant speed down the road, it's not accelerating. Okay, so even if you've got your foot on the accelerator, you're still not accelerating. Not if your speed is constant. So Newton's laws of motion are really built around that picture of motion. And so there were three laws. The first one, that all objects moved in a straight line and a constant speed unless acted on by an outside force. Okay, so that means that if something's moving in a straight line at a constant speed, all the forces on it are balanced. There's no net push. Okay, and we've had some questions in the your turn assignment that ask you about that. On the other hand, if something is accelerating, that means there is a net force on it. That means there's something pushing on it. And then how much it accelerates depends on how hard that push is and how much mass the object is. So it takes a lot more force to move something with to accelerate something with a lot of mass than it does something with very little mass. And then the third law, that's the one that deals with the forces between two bodies. And the key idea there is that those forces are always equal. Okay, that's really big. If something is exerting a force, if something is pushing on another object, the other object is always pushing back with the same force. It doesn't matter how they're moving, whether they're accelerating or not. Third law always applies when you're talking about forces between two bodies. And so that's, again, it's a key one. It helps you understand why things behave the way they do. And so think about that. Think about any time you're pushing on something, that thing is always pushing back on you with the same force. Okay, we also looked at energy. Energy is kind of like a form of accounting in science. It's a way, and really that's a way to think about it. It's a conserved quantity. It's something that you have to, that the total energy stays the same with one sort of exception we'll mention in a minute here. But it depends, but it shifts form. And so you can have energy that is kinetic energy, that is the energy of a moving body. Okay, and that depends on just how much mass it has, how much velocity it has, how fast it's going. But then you can also have thermal energy. Okay, that's heat energy, and heat energy is really the kinetic energy of all the trillions and trillions of atoms that are inside that object. But we measure that energy as heat. So the Kelvin temperature scale is based on this idea of thermal energy. Absolute zero Kelvin, is the temperature where atoms stop moving. That's why you can't get colder. That's why it really is absolute zero. Room temperature is about 300 Kelvin at this in the scale. But then there are lots of kinds of potential energy. And you want to keep these straight. There's different ways of storing energy. One of them is gravitational potential energy. Okay, that's based on how high up something is. So it's the potential to fall. So something that's high up has a lot of gravitational potential energy. As it moves downward, it's turning that into other forms. Okay, there's elastic potential energy. We don't deal with that one too much in this course. Chemical potential energy. And anything you burn has chemical potential energy. The food you eat has chemical potential energy. There's electromagnetic potential energy. So, and there's one really special kind of potential energy called mass energy. And this is that exception I was mentioning earlier. Matter itself, it turns out, has a potential energy to it. And we don't normally tap into that, okay? It's not something you run into in day-to-day life. But when we do have things like nuclear reactions, those release the stored energy in the mass of the atoms themselves. And a little later on, we'll see that this is exactly what happens inside planets like the Earth. This is what keeps the interior of the Earth warm. It's literally a big radioactive generator. There is radioactive material inside the Earth, and very slowly it's decaying and it's released, turning that mass energy into heat. So we'll come back to that. We'll look at that a little later on in the course. That then takes us to the last topic that we've covered this in this part of the course, and that is gravity and orbits. And this is really a whole bunch of applications of all that stuff about forces and energy to the specific force of gravity. And we talked about that force and how we calculate that force. So it's based on the masses that that are feeling it. So if you want to figure out the force of gravity between you and the Earth, you need your mass, you need the mass of the Earth. And then you need the distance between you, which if you're standing or sitting on the Earth like I am, it's the distance between the center of you and the center of the Earth. Well, that's also the Earth's radius. So frequently you will see this formula listed as G m1 m2 divided by r squared, where r is the radius. And that's what you would use to calculate your weight here on the Earth. So that's the formula that we use. As I say, this is what gives you weight. And so we've done some calculations this past week on figuring out how much you weigh on another planet, which you can do. You can figure out if you know its mass and you know its radius. So that's what, and that's what we've been doing. And hopefully you found that, yeah, changing the size of the planet, bigger planets have stronger gravity. And so you're going to tend to weigh more on those than compared to little ones. So then we talked about orbits. And orbits are a really neat application of that gravitational force because they're really giving you a chance to see something that's very big in astronomy, right? Lots of things orbit in astronomy. And it's something which is surprisingly simple. The neat thing about an orbit is there's only one force, and that's gravity. So when a spaceship is in orbit around the Earth, it is feeling just one force, the force of gravity. And of course, you know what gravity does, right? It tries to pull you down to the ground. And that's what it's doing to that spacecraft in orbit around the Earth. And the reason the spacecraft doesn't just fall is because it's also got its own velocity. It got a push. When we put an object into orbit, the hard part is not getting it up there. The hard part is getting it going fast enough so that it doesn't just fall right back down again. And so going into orbit is the real trick with getting moving fast enough is the trick with being in orbit. So you need to get up to a speed. In the case of Earth, if you're just outside of our atmosphere, you need to be going about 8 kilometers a second. That's 8,000 meters every second, just so you don't fall back down and hit you. And that's the speed that speed is what lets you instead fall around the Earth. And as you go around, you're still always feeling the Earth's gravity. You're always falling. You just never quite hit the ground because the Earth is round, and you wind up curving in a curved path that just misses hitting the Earth. So that's orbits. And then the last topic we covered was tides. And tides, again, are an application of gravity. And tides, the key idea behind tides is that gravity gets weaker as you get farther away from the moon. And so that's true of the Earth and the moon. The Earth feels a gravitational pull from the moon, but that force is a little bit weaker on the side that's facing away from the moon versus the side that's facing towards the moon. So if you were on the Earth, if you're on the side facing the moon, then you're being pulled towards the moon a little bit. And that creates a little bulge on that side of the Earth. And in particular, because it moves a lot more easily than rocks do, the water on that side of the Earth tends to bulge out, producing a high tide there. The tricky part, and this is the part that is the biggest challenge to get, because it's almost counterintuitive. The side facing away from the moon is feeling a weaker pull. And so in effect, the whole Earth is being pulled by the moon. But if you're on the side facing away from the moon, you're not being pulled as hard as the rest. And so you're kind of being left behind. And that has the effect of also bulging out. In this case, you're bulging out away from the moon. And so you get a high tide there. So we have 2 major high tides on the Earth, one on one side, one on the other. And then it's going to be low tide halfway in between those 2. So those are the main things to deal with tides. Of course, we talked about a few other things, like the fact that the sun modifies those tides. So the sun creates spring tides and neap tides, which are higher or lower. And what's really happening is the difference between the high and low tide are different. So in a spring tide, when the sun and moon are lined up, you have the high tides get really high. The low tides also get really low. It's the time to go beachcombing. If you're on the beach in a spring tide, you go at low tide, and it's way down. You can see all kinds of cool stuff down there. So that's a spring tide. A neap tide, on the other hand, is when the moon and sun are at 90 degrees. And then when that happens, well, the high tide's actually not very high, and the low tide's not very low. So there's not a big difference between the high and low tide. Okay, and then lastly, we mentioned that tides have long-term effects too. They slow down how fast the Earth is spinning, how they've done that to the moon. That's why the moon keeps the same face towards the Earth all the time. They also can act as a heat source, and this is something that that we'll come back to a little later in the course, because while this isn't such a big deal for the Earth and the moon, there are other parts of the solar system where that tidal heating turns out to be the thing that drives what some of the moons of the solar system look like. So in a month or so, we'll come back to this, and you'll see just how important a role tides can play on moons in the outer solar system. So those are the major topics. As I've said, make sure you practice the questions we've done. Make sure you let me know if you want to go over any of this, okay? If you have questions, you don't have to be sitting there on your own trying to figure it all out. It's okay to ask. That's part of my job. I now teach most of my classes are online, which means that most of my time is available to answer your questions. So come into office hours or just make an appointment, and I'll be glad to help you. All right. Let me know if you have any questions. Good luck on the exam. We'll see you online.